Hello, or rather, good evening, I suppose. What I'd like to talk about today is some of the more precise mathematics that sit behind what I talked about last time. So last time I showed you a Mathematica workbook that I built out that shows things like how to construct things like attracting orbits in cyclic or periodic orbits. And so I thought today what I could do is I could sort of make some of those notions precise, talk about how we compute some of the objects that are related to those, and maybe come up with some of the connections between the c and the z squared plus c and the behavior of the sort of dynamical system that we generate when we iterate that function. So we're going to start by talking about attracting orbits. So first off, remember that a periodic orbit of f of z is equal to z squared plus c is a collection of points. So is a sequence, say z naught up to zm, that has the property that if you start at z naught and you apply f, you get z1, and if you apply f, you get z2, and you continue down the chain until you get to zm. And on the last application of f, zm is actually equal to z naught. So you get back to where you started. So this would be called a periodic orbit of period m. This is a period m periodic orbit. So for example, if you remember the function f of z is equal to z squared minus 1, f of 0 is minus 1, and f of 0 is equal to f of minus 1, which is equal to 1 minus 1, which is equal to 0. So for the function f of z is equal to z squared plus 1, 0 gets mapped to 1, which gets mapped to 0. So this particular sequence is period 2. So this is a period 2 sequence. And yeah, so that's sort of what we mean. There were other functions that we saw in the demonstration that had periods that were longer than that, or at least exhibited behavior that was longer than that. Points in a periodic orbit, points in a periodic orbit called, perhaps unsurprisingly, period points or periodic points. Of period m or f. Now, any point in that cycle is the generator of that same periodic orbit, right? Because if you start at any point in the sequence and you start applying the function, you will eventually wrap back around on the same period. So one thing to observe here is that there's a relationship between periodic points and fixed points. So you can imagine that if you looked at not f of z is equal to z squared minus 1, but f of z, then you would be looking at z squared minus 1 squared minus 1, which is z squared minus z to the fourth, my basic algebra here, z to the fourth, z to the fourth minus 2z squared plus 1 minus 1, and that's equal to z to the fourth minus 2z squared. And if you stare at that for a minute and you calculate its fixed points, so this is the fixed points of f of z. If you take f of z and you calculate the fixed points, what you get is, I would like to know f or z to the fourth minus 2z squared is equal to z. Well, that happens precisely when z to the fourth minus 2z minus z is equal to 0. Z is equal to 0 factors out of that. And it's also clear that if you eyeball that for a second, this equation will be equal to or will be solved for Z is equal to 0. And this term right here, if you put in -1, -1 will solve that polynomial as well. You can check that by plugging in, or if you're really ambitious, you could use synthetic division or something. But you can just observe that that's the case. So Z is equal to 0 and Z equals 1 are fixed points of f of Z. And that corresponds to being period 2 periodic points for the original f. So if you're fixed points for f of Z, then you are period 2 periodic points for f of Z. And so this is not all that useful for more complicated equations or where the periods get really complicated, because you can imagine finding the roots of large complicated polynomials is something that's usually just done numerically. But at least it gives us the idea that we can move back and forth between fixed points of polynomials and periodic points for our sort of Z squared plus C type setup. And so basically that's the idea, that there's a relationship between fixed points. So I guess the big claim here, the upshot, is that you are a fixed point for n iterations of f of Z, and this goes back and forth with being a periodic point of f of Z of period, some period that divides n, so say a period J, where J divides. And so we can sort of fruitfully move back and forth in some contexts. So the next thing we'd like to figure out is how we know if an orbit is an attracting orbit or not. So it's possible to have sort of these orbiting points or a fixed orbit, a periodic orbit, that don't actually pull these orbits into it. Just like there could be fixed points for a function that are repelling fixed points, it's possible for an orbit not to be attracting. And it turns out that the way that you look at that is the same way that we looked at whether or not fixed points of linear functions were attracting or not. We're going to compute a derivative. So first, we'll define what it means to be attracting. So a fixed point Z star of the function f is called attracting there's a neighborhood of that point Z star, so that the limit as n goes to infinity, I guess we call it a neighborhood, say, I don't know, D Z star R. So that's like a radius R neighborhood centered at Z star. So the limit as n goes to infinity of n iterations of f applied to Z. That converges to Z star for any Z in D. So if I can find any neighborhood in that initial neighborhood that converges, then we call that an attracting fixed point. So I guess the idea here is if you start with a point Z, so from picture the picture of this definition is that we have a point z star floating around. So here's z star, and that I can find some disk around that has the property that if I pick any other point inside here and I start calculating its orbit under F, so if I start at z naught and I move over here to z1 and I move down here to z2 and over here to z3 and so on, but the idea is that that's sort of being pulled into the fixed point. So if I can find a neighborhood where everything in the neighborhood gets sucked in, that's called an attracting fixed point. And likewise, we're going to say that we're going to define what it means to be an attracting orbit, periodic orbit, by referring to that sort of interchange between fixed points of a function and periodic points of a smaller function. So what I mean is we're going to make the definition of a periodic orbit say of period m consisting of the points z naught up to zm, which is equal to z naught, is attractive or attracting if n compositions of f, I guess we should be careful here. If Zn is an attracting fixed point for n iterations of f. And so that's sort of your basic definition. So you are an attracting orbit for f if you're an attracting fixed point for n iterations of f. Okay. So the next thing that we need to do is some sort of number that we can compute that describes when this happens. And so when we were working with the linear functions, we calculated the derivative, and that told us that, so I guess the idea here is, how do you know if a particular fixed point is attracting or not? And so remember that we looked at those linear functions. L of z is equal to az plus b. If you calculate the derivative, you get L prime of z is equal to a. And it turned out to be the case that if the modulus of a was less than 1, then you were attracting. And if the modulus of a was greater than 1, then you were repelling. And we're going to do the same thing here. We're going to use the derivative. We're going to evaluate it at a fixed point. We're going to notice that if we do that, we're essentially constructing the linear approximation for the function at the fixed point. If the a value is less than 1 in modulus, it means that you're spiraling in. If the a value is larger than -1 in modulus, it means you're being pushed away. And that's the content of the next definition. So the multiplier of a periodic orbit z naught z1 up to zm, which is equal to z naught, is defined to be, we're going to use the number lambda to stand for the number that we're going to compute. And what we do is we just calculate f prime of the first number times f prime of the second number times f prime of the third number, and we just go up the chain until we get back to f prime of zm minus 1. Now, of course, we don't have to compute the derivative at zm because we've already thrown it into the mix right here. Remember that z naught and zm are supposed to be equal to each other. And that's how you compute it. So lambda is called the multiplier. Lambda is the multiplier. And you just check the modulus. It turns out there's a theorem that says that if that multiplier is less than 1 modulus, then the orbit is attracting. So here's our theorem. This is actually got a name. This is called the attracting periodic orbit lemma. It says, unsurprisingly, since we already know there's this relationship between periodic orbits and fixed points, that a periodic orbit is attracting if the multiplier lambda, which is equal to f prime at z naught up to f prime at zm minus 1 has modulus of lambda less than 1. So here's the basic idea of how this proof goes. What you do is you say, all right, we're gonna start by choosing some point in our orbit, right? So you can imagine that we look at zi, which is one of the points inside of our periodic orbit. And then what we're going to do is we're going to consider the fixed point instead, right? So we're going to lift this up so that we're looking at something like f to some suitable number of iterates so that this zi is a fixed point here. So you pick some iterate of f so that this equation holds. And then you basically construct the function something like g of z is equal to the nth iterate of f evaluated at zi, and then you subtract, or it's z. And then you subtract off zi. And the reason that you do that is because now this is a function so that g of zi is equal to 0. And once you have that in place, you can basically expand g as a power series. But since g at z around zi, but since g is 0 at zi, then g will expand as a power series. Generally, g of z is going to expand as something where you have lambda times z minus zi, and then some other sort of higher order crap that you don't care about. So a2 times z minus zi squared, and so on. And the idea is that if you get really close to the point zi, these terms are all small. And so close to the point zi, this function g of z looks like lambda times a linear piece. And that's what gets you the connection here, that since g of z is approximately linear when you're close enough to zi, so that these terms over here are very small, then the upshot is that the lambda that you get there, which is the value of g, right? It's the derivative of g. That sort of controls whether or not you're attracting or not. So you can read this proof in the rotor notes, but this is the basic idea: is that you're constructing a power series in such a way that there's no constant term, and you can pay all of your attention to this sort of linear approximation, which is what's going to dominate the power series when you're very close to the point that you've centered at. Okay. So the next idea that we need is an idea called the basin of attraction. We mentioned this yesterday in the notes. If you use a sort of fancy letter, I guess we can use the letter O here to stand for the orbit z naught to z1 up to zm, which is equal to z naught, just to give it a name. Let's suppose this is an attracting orbit. Then we can designate a set A sub O to be equal to, so we're going to designate this the basin of attraction. And you can think about this as the set of all points that if we feed them into F and we iterate them, then they get pulled into that periodic orbit, just like we saw in the mathematical notebook last time. So we'll pull that up in a second here. In fact, maybe I will share my screen and we'll take a look at this. So if you look at this, the basin of attraction here, the basin of attraction to that fixed point is the set that's inside this curve. This is what we mean by the basin of attraction. It's all of the initial points that when I start iterating, they get pulled into the fixed point. And likewise here as well, right? The basin of attraction is the set of all points that get pulled into that periodic orbit of period 3. So let me pull my notes back up again. And we'll reshare. So I want to share my screen. You guys get to see the nitty-gritty of flipping screens back and forth here. Okay. And so we can actually formally define the basin of attraction mathematically as the following. So we say that the basin of attraction is equal to the set of all complex numbers C that have the property that as I repeatedly iterate my function f, on Z, that this thing actually ends up running in to Zj, then goes to infinity. For some J, it's supposed to be a J, instead J and wrote I. For some J in the set of points 0 less than or equal to J less than or equal to M minus 1. So the content of this definition is the basin of attraction is the set of all of the points in C that end up pulled into some point in the orbit. And then by the immediate basin of attraction, that's just all of the I guess we could say the immediate basin of attraction. That's the union of connected components of this basin that contain the orbit, containing Z0, Z1, up to Zm minus 1. So it's the sort of subset where we take all the bits that are connected to each other and then we glue them in. So it's not always the case that these sets are connected to each other. And so sometimes we want to say, take just the bits that contain the period, and then those things are what are called the immediate basin. Let's see some more complicated examples of that further on in the course. And so that's the basic idea. And the sort of last thing that I'll mention here, because it links up with conformal maps, is it turns out to be the case that part of the reason why these theorems are so strong is because conformally, locally, these maps are linear locally, at least conformally. So what we say is this is a powerful theorem called Koenig's theorem. I invite you to read this. I'm going to state it here, and then we can talk about it when I get back. The idea is if you suppose that you have some fixed point, it's attracting. So suppose this is an attracting fixed point. of a polynomial f with multiplier lambda not equal to 0. So you have to stay away from those derivative 0 points. Remember, we run into those before. Those are places where conformal maps like fall apart. I mean, so if we have non-zero derivative, then there exists a neighborhood U of our point and a conformal map phi that takes that neighborhood U over to the range set phi of U, so that for any W and phi of U, so that is if I transform over to this U set, we have phi composed with F composed with phi inverse of W is locally equal to lambda W. And what this says is, under this conformal change of variables, F is essentially a linear function on this neighborhood. Remember, what conformality is doing is it's distorting that circle possibly into some other shape, but it's preserving geometry. And so this is a geometry preserving map here. So whatever F is actually doing, if I can restrict my vision tight enough and I do a conformal change of variables, F is actually secretly a linear function on that neighborhood. And that is precisely why the multiplier is controlling whether or not you're coming in or being pushed out. Okay, so yesterday was a play with Mathematica day. Today is sort of a heavy slog through the technical definitions of how all these things work. My goal for the next time is to start playing around with what the Mandelbrot set actually is, and we're going to build it up from the inside. We're going to start by figuring out what all of the C's we can plug into Z squared plus C that give us fixed points, and then we'll look at the C's that give us attracting orbits of period 2. And then we can look probably at what C's give us attracting orbits of period 3. And then the math gets so hard that you have to use a computer to produce the rest of it. But that's the goal. So we're going to start looking at how we can connect. So next time, we're going to look at the connection between the value of C and the existence of periodic orbits of period 1 and period 2. All right, thanks for watching. We'll see you next time.